All right, so today we're really going to focus on energy and how energy helps us understand the physical and chemical properties of substances. All right, so let's look at these examples. What are these different images pictures of? We have a cube of something, we have a beaker filled with something, and we have a volumetric flask that is capped. All right, so what are these images? Well, solid, liquid, and gases. So the first example is a solid. Notice it has a definite volume and a definite shape. If you were to place a solid onto a counter, what would it do? Would it kind of ooze out and spread? No, it would retain its shape. All right, and it does not have a volume that changes just because you put it in, an open area. Okay, so it's got a definite volume and a definite shape. As a liquid, what happens if you put liquid onto it? It will assume the shape of its container, and in that case, it will just spread out, filling every nook and cranny that it can find. All right, but you still have a volume. If you have 3 liters in a beaker and you pour 3 liters onto the table, guess what? You have 3 liters on the table that you now have to clean up. All right? So it has a definite volume, but it does assume the shape of its container. The next one is a gas. The gas assumes the volume and the shape of its container. That's why we had to cap the volumetric flask. If you did not cap that volumetric flask, those gas molecules would be spreading out and taking on the shape of its container, whether it be a big, huge room or a volumetric flask. All right? So when we're thinking about all of these different atoms, depending on which phase they're in, they're still moving, okay? How much energy do the atoms have in the solid phase compared to the liquid phase compared to the gas phase? Which one's moving the most? The gas phase. Those molecules have a whole lot of motion. They're bouncing around, they're hitting each other, okay? But in the solid phase, are they rigid? Are they not moving at all? No, they still have some energy, as long as they're not at absolute zero. If they're at absolute zero, remember that's where your temperature is so low that you've stopped all movement of molecules or atoms. Okay? So, since we haven't reached absolute zero yet, all solids, the atoms of them are still moving somewhat. Okay? So what does that mean? For us, it means whenever you're changing from a solid to a liquid to a gas, what do you have to add? You have to add energy. And that energy is movement. That energy is contributing to the movement of the molecules that allows it to take on the new property of being a liquid or being a gas. All right, so if we look at it with this molecule, we can now give names to each phase transfer. All right, so from a solid to a liquid, whenever you add energy to a solid, it's termed melting. When you add energy to a liquid, you are evaporating, okay? Or evaporation is the term to change from a liquid to a gas. Notice you're adding heat, which is the same thing as saying you are adding energy, okay? Because energy is directly correlated with heat. Energy is the movement of molecules. What happens when you increase the temperature? Your molecules gain that energy and transfer it into movement, okay? When you go back the opposite direction from a gas to a liquid, that is condensation. And when you go from a liquid to a solid, it's freezing. Okay? Now there are 2 terms that I've written up high and down low. Whenever you go directly from a gas to a solid, that's termed deposition. An example of this would be in research, for instance. Sometimes you want a really, really thin layer of a solid sample. So like let's say you wanted a really thin layer of a gold. Okay? So you want it so thin that you maybe only have 1 atomic layer of gold laid down on something. For example, like etching or making really small pieces for computer parts. Okay? What you can do is you take a gas and you shoot it. You give it so much energy, you shoot it at a solid sample. Whenever that gas hits that sample, it immediately stops it, transfers that energy. All of that energy is removed from the sample and it immediately changes from the gas phase to the solid phase. So that's deposition. Then when you go from a solid to a gas, if you're to do the opposite, that's called sublimation. And basically, you're adding heat so quickly, it's turning from a solid into the gas phase. And that's what happens on top of a mountain whenever you have snow. If snow, instead of just melting into a liquid, if snow turns into the gas phase, you have sublimation occurring. All right, so let's look more at evaporation. Evaporation is when you're changing from the liquid phase to a gas phase, and condensation is the reverse of that. So let's look specifically at this picture in the right-hand corner. What's going on here is as molecules, they're in the liquid phase, which has less energy than the gas phase, remember. Whenever liquid water, so when an atom gets to the surface, it could have so much energy. It overcomes the pressure that's holding it in. There's a little bit of surface tension on the film. Whenever it overcomes that, if it has so much energy, it can actually escape, okay, and turn into water vapor, which is the gas phase. Whereas the opposite happens. With all the water vapor in the air, if one of them collides with water, it can lose energy and condense and join the rest of the liquid water that you see here. All right, so if we look at this from kind of a kinetic energy model, what's going on here is once it has sufficient energy to overcome what's called hydrogen bonds, then it can escape. Now, what are hydrogen bonds? We'll get to that in a much greater detail later, okay? But for our sake, if you look at the structure of water, we'll just talk about it in a general sense today. You've got an oxygen atom attached to a hydrogen atom, attached to another hydrogen atom. And your oxygen actually has 4 electrons that are free, still onto the oxygen, that are not bonded to anything. Since these are electrons, the oxygen has a partial negative charge, and the 2 protons, the 2 hydrogen atoms, have a partial positive. So what happens in solution is if there's another oxygen atom attached to hydrogens, another water molecule, then guess what? The oxygen has a partial negative, the hydrogens still have a partial positive. You can actually have the oxygens of one atom interacting with the hydrogen of another atom. And that's what's called our hydrogen bond. Okay? So that is our hydrogen bond. And what that is, that's a strong bond. It's not nearly as strong as the bond that naturally exists in the water molecule itself, the hydrogen to oxygen, but it's still really strong. So it's trying to hold all of the different water molecules in the water. But every now and again, one water molecule or multiple water molecules have enough energy that they can escape that tension that's holding them down. Okay? So as you're cooling that water, this high-speed water molecule, it can actually re-enter into the gas phase. So kind of the idea is if it's got enough energy, it's going to approach the surface. Okay? If the rest of the liquid is cooled, it now has more energy in relation to the water, and it will leave into the air phase. Okay, into the gas phase. Once they've entered this gas phase, they lost a lot of the energy that has taken place via hydrogen bonding, as noted here, but it's now entered into the gas phase, okay, where it actually has more energy as the gas phase, but because it was at a lower temperature, it helps to cool the air, okay, because the liquid was at a lower temperature, a lower energy state. The gas was at a higher energy state. So if you have a particle that was part of the lower energy state entering into the higher energy, it's going to help cool the air a little bit. Okay, so if we kind of think about this, let's think about sweat, for instance. Condensation and evaporation occur at the same time at a liquid surface. So if you're sweating, for instance, why do you sweat? Pigs, for instance, they don't sweat, so they have to go roll around in the mud in order to cool down. Whenever we sweat, that's a cooling process. If you think about it this way, all of the sweat molecules on your skin, they'll evaporate. They were nice and warm. When they evaporate, they pull that energy with them as they leave. So they pull energy from your surface, which is the same thing as pulling heat from your surface. So it's a cooling process. So sweating helps cool you down. Okay? What if you're in a really humid environment? You went for a run, let's say. You are sweating, you're gross. Okay? You're still going to have as much sweat on you as when you finish the run. It's not going to just magically evaporate. But if you're in a really humid, non-humid environment, a really dry environment, that sweat's going to evaporate off you faster. Okay? Why is that? And the reason for it is because condensation and evaporation can occur at the same time. So whole lot of gas, water vapors floating around in the atmosphere, then your skin, the water that's on your skin is not going to evaporate as fast because you already have a really dense amount of water in the air already. Whereas if it's a dry environment, it's going to want to evaporate quicker because there are not as many molecules. If we were to think about this kind of as like a beaker. Okay, let's put 2 beakers. And for the sake of this, we're just going to say each one has 5 atoms of water in the beaker. This is an oversimplification of this. Okay? Obviously, a beaker does not contain just 5 atoms. Okay? So that's our water. Beaker A, we're going to put a whole bunch of water vapor in the air. Beaker B, let's just put 1. Okay? So this would be like your dry desert environment. This would be your really humid Nashville environment. Okay? Which one of these is the water molecules going to want to evaporate at fastest? Are these going to want to join? Or are these going to want to join their gas phase brothers and sisters? And B, they're going to want to join a lot more quicker because with A, you kind of already have an equilibrium. For every 5 molecules of water in the atmosphere, you already have 5 molecules of water in the liquid. So it's pretty content. Okay? Whereas in the dry environment, you have 5 molecules of water in the beaker and only 1 out high. So they're going to keep on evaporating until you reach more of an equilibrium state. Okay? But does that mean in your human environment that you're never getting evaporation and condensation? Let's say you leave liquid out like just a cup of water. What's going to happen? If it's a dry, hot, dry environment that's really hot, that water is going to evaporate. You're going to see the volume of your beaker decrease over time. But let's say it's a really humid environment. You leave your beaker out and nothing happened. It never evaporated. Is that because you never saw it never evaporated, stuff never condensed? No, it's that condensation and evaporation happened at the exact same time. So for every water molecule that evaporated, you had 1 that condensed. Okay? Whereas in a dry environment, you had the rate of evaporation is a lot higher than the rate of condensation, so that's why it evaporated quicker. Okay? All right, so this is kind of that same question. If the water level in a dish of water remains unchanged from one day to the next, can you conclude that no evaporation or condensation is taking place? And that's what we just discussed. So if you were to put it in just kind of a way to write it down in words, not at all. For much activity is taking place at the molecular level. So all of this is about energy at the molecular level. Both evaporation and condensation occur continuously and simultaneously. The fact that the water level remains constant instead indicates equal rates of evaporation. All right, that's the important part. It's not that one's happening and the other one's not. It's that you've got equal rates if you have no evaporation. Whereas if you see your water evaporate, then your rate of evaporation was higher than your rate of condensation. If you see the opposite, if your volume somehow increases, then your rate of condensation was higher than your rate of evaporation. So the number of molecules leaving the surface by evaporation was equal in this instance to the number entering the liquid by condensation. Okay, so let's talk about boiling. Boiling is evaporation below the liquid surface. What's going on is that when pressure inside the bubble equals or exceeds the combined pressure of the water and the atmosphere, it's going to boil out of the solution. It's going to leave the liquid and it's going to enter into the atmosphere. At lower temperatures, at higher altitudes, then water is going to boil quicker. Okay? So for instance, in Denver, which has an altitude of 1 mile, water boils at 95 degrees Celsius, whereas at sea level, water boils at 100 degrees Celsius. Okay? So if we kind of think about it this way, at Denver, is there more pressure on the water or less pressure on the water? Less pressure on the water. Why is that? It's 1 mile altitude, so the amount of molecules pressing down on Denver, which is our mountainous city, is not nearly as high as it is at sea level. Okay, there's not as many molecules in the atmosphere at Denver as there are compared to, say, Louisiana. Okay, so what's going on is there's not as much pressure outside of the boiling pot of water. So in order for the water to have enough energy to want to escape the water, all it has to do is it has to have a pressure equal to the atmospheric pressure that's combined with the water. So if you have a lower pressure outside of the pot, it's not going to take as much energy to equal the pressure that is outside of the pot. So if you've got higher altitudes, boiling is going to occur at lower temperatures because it doesn't take as much energy to reach that similar pressure state. Okay? Here's kind of a diagram showing how it works. All right, as the liquid is heated, molecules gain enough energy to evaporate beneath the surface. So what's going on here is it's actually evaporating, okay? But once it evaporates, you have to somehow get it to the surface, okay? Before the boiling point is reached, the pressure of the water vapor inside the bubble is less than the sum of the atmospheric pressure plus the water pressure. As a result, the bubbles of water vapor collapse. Okay, so if it's formed but pressure isn't great enough, it starts to dissolve. Okay, so that's kind of your strength state. Okay, but if the pressure of the water vapor inside the bubbles equals or exceeds atmospheric pressure, the bubble is buoyed to the surface. Okay, and it can escape. Right? You see evaporation down here, which is what we call boiling. All right. So what you have to do here is you have to have a couple things. You have to evaporate the bubble. Then the evaporation, the bubble inside of it, the water vapor that's produced underneath the surface, has to have a pressure greater than what's outside of the boiling water. And if it does, it'll go to the surface and escape. All right. Now this might be a little bit counterintuitive, I find. Water is a cooling process. So just as sweating is a cooling process, boiling is a cooling process, okay? What that means is for every atom, every molecule that enters into the water, the water vapor phase, the gas phase has more energy, right? So whenever the liquid turns into a gas, the gas particles have more energy. What do? They then leave the beaker. As they leave, they take all that energy that they found and that they collected, they take it with them. And as they pull energy from the surface of that liquid, the water's some amount of energy, average energy, is lowered. Okay? That's why you can't boil water at 105 degrees, okay, as far as the normal operating conditions go. Okay? So the idea that as energy is removed from the water, the rest of the water is cooled from it. Okay? You're still applying heat to get the bubbles to occur. What we're talking about is the relationship between the water and the vapor molecules that entered the gas phase. All right, so what we've got here is a diagram that explains how the different energies correlate with the heat. What I mean by that is we start out with ice. It melts, turns into liquid water, evaporates, turns into water vapor. So we've got the solid going to the liquid, going to the gas state. If you notice, temperature increased as we went from left to right. Why did it increase? Because heat is being added. Okay, but let's think about this a little bit. So if we have ice, ice is ice until 0 degrees. At 0 degrees, it's not going to ever turn into a liquid until it's higher than 0 degrees. From 0 degrees, it remains water until the point of which is 100 degrees, which is its boiling point. Okay? So what in the world is happening at this point? This melting phase. Okay? And this melting phase, this is the amount of time that takes place between when an ice is solid and an ice is liquid water. So what you've got is the ice is actually rearranging its structure and slowly turning into a liquid. And so that takes heat to rearrange those molecules so that they're ready to go to the liquid phase. So at 0 degrees, the second you hit 0 degrees, it doesn't instantly turn into water, unless your energy was sufficient to overcome this energy barrier of 335 joules. Okay? But there's still a period of time at which the ice is turning into a liquid. Same thing for evaporation. There's a period of time at 100 degrees, which is the boiling point, where heat needs to be added to finish that transition from water to water vapor. All right? So kind of the idea here is in the melting phase and in the evaporation phase, all of the heat that's added is not being added to increase temperature. The heat that's being added is to help transition between one phase and another. Okay? So if I the star indicates heat aiding transition or phase change, we'll say. And not a change in temperature. Okay? A positive heat added, a positive number in joules, indicates that heat was added to the system. It makes sense. If you're adding heat, you should be melting or evaporating the sample. If you are removing heat, or if heat is being released in the process, it's a negative energy process. Okay? We have names for that. Let me see if I put those up on here. I did not. Okay? So if we have a positive energy change and we're adding heat to the system, it's going to be endothermic. It requires heat. Okay? If heat is being released in the process, it's called exothermic. Okay? So notice evaporation, melting, are those endothermic or exothermic processes? Those are endothermic processes. Think about it and consider by yourself, what would be the names of all those processes that are exothermic? Go back to that heat released, heat added diagram and think about which ones are endothermic and which ones are exothermic and why. Basically, anytime you need to add energy to get the molecules moving more, it's going to be an endothermic process. So kind of as a recap for today, sample solids to liquids and then to gases based upon the energy that is added or removed from the sample. So really for today, we really tried to focus on energy. There are names for each of these energy changes. Can you name them all? Boiling is evaporation below the surface. So the idea is that evaporation happens normally at the surface, but if it happens below the surface, we have a special name for that, and it's boiling. The gas phase is the most energetic phase. A cooling process removes energy from the system. Can you name a couple?